Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to discuss the lecture number 16, and during this lecture we will discuss about procedures. What are the concepts behind the procedures, and how we can implement, how we can use procedures in assembly language, and what is the discussion, all over discussion behind these procedures. Before going to start lecture number 16, we will revise what we did in lecture number 15. So during lecture number 15 we discussed the stacks, how we can use those stacks, like different instructions related to stacks. We did some examples in assembly language that were about the stacks, how to maintain, how to add information inside the stack, and so on. So basically, what was the stack? A stack is a data structure which is LIFO structure, last in first out structure, as you can see here. So in this stack, all the items or elements are added from the top and also removed from the top, and it's a last in first out structure, that the element which has been added in the end will be the first element get from this structure. This stack is managed by the CPU using two registers. In case of real mode, it's different, and in the protected mode the way is different, but usually CPU uses two registers. Those registers are stack segment and the stack pointer register. This stack pointer register basically serves as this top pointer, or the pointer which handles the addition and deletion of the elements. There were two instructions that we will mainly use also in the forthcoming lectures. Those instructions are push and pop instructions. Actually, the push instruction, its syntax is also given here. We already discussed this syntax, that we can add elements inside the stack, and those elements, like there can be registers or memory content, like the values of the variables and so on. So these registers can be 16-bit or 32-bit, or it can be immediate value or the constant value, or it can be a 16-bit or 32-bit variable, and so on. On the other hand, we have the pop instruction. This pop instruction retrieves elements from the stack. Those retrieved elements are stored in register, that can be 16-bit register or 32-bit register, or they can be stored at some memory location which is pointed out by the variable name or any address. Now here, before going to push, a stack pointer is added or incremented the size of the memory element, or the element which we are going to store, and then it has been written inside the memory. On the other hand, pop instruction, what it will do, it will first read the value from the location which is pointed out by the stack pointer, and the combination of stack pointer and stack segment are in the flat memory architecture only by the stack pointer, and then it will decrement. So the operation is totally reverse. And we also discussed that all the elements that we add, for example, element number 1, element number 2, 3 and 4, so 1, 2, 3, 4, they are added like this one. For example, fourth element has been added first, third element, second element, first element. Then the operation of pop will be reverse. Means fourth element which was the first element which was added in the end, that will be the first element to be popped, and so on. So the element that was added in the last will be the first element to be retrieved or popped from the stack. So along with the other instructions like push and pop, there are some other instructions like push FD and pop FD. This push FD and pop FD, these two instructions, they are used to push and pop the flag registers. For example, if we push some value inside the we perform some operations on some registers, definitely the flags are also affected. And if we call, or if we transfer control to somewhere else, then before going to transfer control, what we do, we first push all those values of registers along with their flag status. Then we perform some other operations, and when we return back, then we continue the normal execution. There is another instruction that is called the push AD. This push AD instruction saves all the registers or general purpose registers, which include EX, EBX, and up to all these which you can see in this stack. And then there is pop AD. This pop AD perform the same operation, perform the reverse operation like to pop all the all the values of these general purpose registers from the stack in reverse order, and in the order in which push AD has stored all the registers. Then pop AD will pop all those in the reverse order, and so on. So this was the introduction about discussion about the previous lecture number 15. Now in this lecture we will discuss about procedures, how we can define procedure, how we can use those procedures, and the topics that we will discuss. Like first we will discuss how we can create procedures, then how we can document those procedures. For example, how we can use additional information inside the procedures, so that if anybody else or if any other programmer who want to use our procedures or the code, he can easily understand, and what type of information that should be documented, that we will discuss. And then we will discuss about the some of the example where we just use the array sum. In previous lectures we discussed how we can perform array, some of the elements of all the elements of this array. So by using these procedures we will perform the same sum. So how we can modify that program to perform the same operation. Then we will discuss about the call and return instructions. These call and return instructions are used to call the procedure and return from the procedure, and so on. Then we will discuss about the nested procedure calls, like how we can call a procedure from another procedure, and so on, etc. Then local and global labels that we use for jump, conditional and unconditional flow control instructions. And then procedure parameters, flowchart, how we can show our represent our whole procedure in form of a flowchart. Actually this topic is not part of this lecture or part of the subject. You will understand the flowcharts, but how we can document or how we can write flowcharts. So there will be one slide about the flowcharts and so on. Then the last one will be the uses parameter. Now we are starting with the creation of the procedures. Why we need procedures and what is the purpose of these procedures? Actually, when do we have a task that is very large enough, so what we do, we divide that task into different parts. Like for example, take the example like there are different in a whole classroom there are 20 or 25 students, and we assign them some task. Okay, so this part of the project will be performed by this group, and this part of the project will be performed by this group, and so on. So a complete project, we divide that complete project into different sections or different parts and assign the task that each group or each person will perform this task, and so on. Similarly, what we do, if we have a larger program, then we divide that program into smaller tasks. Our larger problem is divided into smaller tasks. Why? What is the reason? To make it more manageable. So if one person or if a large program is there, it's really difficult to track all the logic in single program. So we divide that program or the problem into smaller tasks or the procedures, and so on. So the procedure in assembly language is almost similar to the other languages like Java, C, and whatsoever the high-level languages you can recall. So for example, C or C++ or Java, we define procedures or functions. We define functions and we use them in our main program. Similarly, we will define procedures in assembly language and we will use them in our main program, and so on. Then next is the very simple example. This example demonstrates how we can create a procedure. For example, we are going to create a procedure, its name is sample. So this is the name of the procedure, for example. So this is the name of the procedure, sample. And if we want to create a procedure, first we will write the name of the procedure and the keyword PROC, P-R-O-C, PROC. So this statement is the starting point, that our procedure starts from here. Then we will have the body, or there is a body of this procedure, the activities, the actions, or the task that you want to accomplish. So all the instructions that are dedicated or that are planned or that are assembled to perform that task, sequence of instructions, proper sequence, that should be inside this body. And then at the end, if we want to return from this procedure or transfer control back to the main program, so we will use return instruction or statement. And the end of the procedure is identified in a similar manner, like we will write the name of the procedure and then end P. So procedure, P-R-O-C, and end P, these are the keywords. Along with the name of the procedure, same name of the procedure are used to create a procedure. Now, this was about the creation of the procedure, and then next we will discuss what is the documentation. For example, if we write a procedure and we store in some library, for example in the library files, lib files or include files and so on, and if someone else, they want to understand or they want to recall or they want to use or they want to make some modifications inside that procedure, then they need some information that what is the purpose of this procedure, what type of registers are being involved in this procedures, and so on. So to document, the suggested document for each procedure include description of all the tasks that are being accomplished inside the procedure. There should be a small description. For example, this procedure or the procedure accomplishes or compute the sum, its computes or generates a Fibonacci sequence or so on, whatsoever, or it performs some addition, subtraction, integral solution, and so on. So there should be a small description. Then there should be about the receives, what information or a list of input parameters that it receives from the main program or from the other procedure calls and so on. So list of input parameters, they state their usage and requirements. For example, if we want to use EBX, ECX registers, what should be inside EBX register or what should be inside ECX register or other registers which we use inside the programs. And returns, the returns means when the procedure performs tasks, some one task or multiple tasks and so on, then what will happen, the procedure returns some value. For the example is, if we perform sum of the array, sum of all the elements inside the array and so on, so we can say that the total sum or the final sum will be in some register like EAX or EBX and so on. So we should mention or we should describe the values that are being returned by the procedures and so on. And requires that what procedure require, like for example, there's some optional list of requirements called the preconditions that must be satisfied before the procedure is called, like push, pop, and something. If we want to reserve or store some values of some variables which are being used, so there, what are the requirements to call this procedure and so on. So this is the optional list if you want to include in. Actually, all this documentation is optional, but the better practice is you should document all the procedures, their purpose, what are the input values, what are the output values, what is the purpose of procedure, and so on. So this is a very good programming practice, even not in assembly language, but in all the languages that you will learn. So you should have to follow this practice. So this is example of sum of procedure. For example, here we want to sum three values or values inside the three registers. So the name of the procedure is sum of. Okay, so here you can see the name from here, sum of procedure, and the procedure starts. And before that, there is a here you can see at this point here there are comments. So all these documentations, they are used in form of comments. Actually they don't have to do anything with the computation or the tasks or whatsoever the operation of this procedure. They just define that what's the purpose and what are the input and output requirements. So here you can see what we documented here: calculates and returns the sum of three 32-bit registers. Okay, what does it receive? It receives EAX, EBX, ECX, the three integers, and they may be signed or unsigned whatsoever. Returns EAX, so the return value is inside the EAX. What is inside EAX is a sum, and the status flags, carry and overflow, etc. are changed. So this is description. What does this do when we return? So for example, if you want to use this procedure, what you should have to do is, first of all, you have to push all these values inside the stack, like EAX, EBX, and ECX, and also you have to push the flag register and so on. And it requires nothing, so there is no other requirements for this procedure. Inside this body of this procedure, there are two instructions. Before calling a procedure, we must have three values inside these registers: EAX, EBS, and ECX. So we are going to add these three registers, like EAX. EBX is added with EAX, and again the result is stored in EAX. Next, what we are going, ECX, the value of ECX is being added in EAX. So the final sum is inside EAX. Now if you want to see the contents of EAX, so they will be as it is. The total sum of these three registers will be inside EAX, and then return. So this is the end of NP. So this is the last statement. Sumup is the name of this procedure, and NP is the directive to indicate the assembler that this is end of the procedure, and so on. Now that was the example about very simple procedure, how we can use that one. Now what we are going to do here, there are two other instructions, call and return instruction. Now the call instruction, this instruction calls a procedure. What does it do when we call a procedure? It pushes offset of the next instruction on the stack. Now you know the instruction pointer, the value of instruction pointer register. For example, if we are performing a continuous task inside a main program, and for example here we call a procedure, at this point we call a procedure. Actually procedure is somewhere else inside the program. So instruction pointer is here, continuously monitoring or locating the instructions. When it comes here, what will happen? Instruction pointer will be updated with the new value, or the value from where this procedure starts. So we will see the example, and then next for next step of this call instruction is that it copies the address of the called procedure into the EIP register, because first it stores the value of this address, current address or return address, inside the stack pointer and then inside the stack, and then instruction pointer is updated with the new instruction which is going to be executed, and so on. Then these are the it copies the new address for this procedure, and it starts execution from the first instruction of this procedure, and so on. So this is about the call instruction. What about the return instruction? When we return from the procedure, the thing is reverse procedure, reverse operation will start. What operation is? It pops the top of this text from the EIP into the EIP. For example, the instruction, next instruction which we are going to store, its address is being popped from the stack and assigned into the EIP, so that the normal execution of program just continue. So there are two instructions, call and return instruction. Call instruction is defined inside the, or used inside the main program, and return instruction, as we saw in our previous slide, that return instruction is the instruction inside procedure which returns the control back to the main program. Here you can see call and return example. For example, this is our main program here, from here to here, and this is our procedure. So here you can see we have a main procedure, our main body of the program is starting with the main, and name is procedure, and then we have called the my sub procedure from the main, and we are performing other instructions or other operations. Then this is the starting of the main procedure, my sub procedure, and this is the end of the my sub procedure. What will happen here, for example, the first instruction inside this main program, its address is 000, all 0 and 20, and next instruction starts from 25 and so on. So what will happen, the 0025, because when we are executing this instruction, then we know that instruction pointer has this address inside it, because instruction pointer is being updated for the next instruction that is to be executed. When we are executing this instruction, before executing this instruction, actually instruction pointer points to this address, but after, when we perform execution, during that point instruction pointer is updated. Means before finishing this whole instruction, this instruction pointer is being updated. So we know that the instruction pointer has all these zeros and 25 in hexadecimal address inside it. So this the instruction immediately following the call instruction is this address. What will happen when we know that this instruction, the first instruction inside this move EAX EDX, this is the first instruction inside the procedure, so execution will start from here. So this is the 000, all the 0 and 40, for example. This is the address. So when we call, then instruction pointer actually has this address. So this instruction, this address will be pushed inside the main, inside the stack, and instruction pointer is assigned a new value. This value will be the address, first instruction's address inside the procedure to whom we are calling. Here you can see what will happen when we perform call and when we perform return. So here you can see the address, the call instruction, this pushes the all this 00 and 25. This is the next instruction after the call inside this text. So this is the address that represents or that shows or that where our next instruction is stored inside the main program or in the code segment. So this stack pointer or this stack is pushed, this address value and so on, and instruction pointer is assigned this new address 000, all the 0 and 40 and so on. So this is after call, when we execute call instruction. Next, when we perform, when we execute or when the assembler executes return instruction, what will happen? So the return instruction, it will pops this address 00 and all these 025 from the stack into the instruction pointer, because so this has been popped into this one. Whatsoever the previous value for instruction pointer is, this will be updated with this one when we execute the or when compiler comes to the return instruction and so on inside the procedure. So this is the example. Now in case of nested procedures, what will happen? For example, this is the main program. Inside this main program we are calling sub1 or the sub procedure 1 or sub1, and then this sub1 procedure is being called. So before going to call this sub1, return to the main program, the address of the main program is being added here, the instruction pointer, and maybe it's possible maybe other parameters, but at least instruction pointer or the next instruction, whatsoever the next instruction is, its address must be code segment address should be stored here, and inside the stack. So I can write here, this is the stack, Now what will happen when we are executing this procedure and so on, and if we are calling the next procedure, its name is sub2. So before going to call this sub2, the next instruction that will be performed inside this sub1 will be stored. So return to sub1 is also stored here. After that, when we call this sub2, what will happen here, you can see from the sub3 we are again calling from the sub2 we are calling sub3. So what will happen here, the return to sub2 is being stored inside the stack. Now what will happen when this return instruction, or when this procedure completes its execution and we return control back to the calling procedure or back to the next instruction from where this procedure was called, like from here to here. So first we will take this or pop this value from the stack, and then we will go back to sub2. Similarly, when this return instruction is being executed, so again we will pop the next the top value from this ESP. Basically, when we are popping this one, then a stack pointer will come here, and again when we call another instruction or this instruction executes, we will pop this instruction and instruction pointer will come here, and when this procedure stops its execution and comes here, then we for sub2, then we will exit return to the main program and so on. So this is the way we use the nested procedures in our in assembly language. Now local and global labels, as we know that these labels we use to transfer control inside the program. For example, we define label 1 here. You can see there is label 1. This is, you can remove this one. So label 1 is here. What we do, we can jump somewhere to label 2 and so on, or label 1, for example JMP L1. I can remove this one, for example. Okay, I can erase. So here, for example, we have the jump L1, so we can jump here. On the other hand, there is a problem when we use procedures, like some procedure of, so the variables or anything which is being used inside the procedure. So the concept is the same concept we used in C or C++. So this label is local or is global, and for example this is local, or L2 is a local procedure. So inside the main program, whatsoever the labels you define, they are global and they can be accessed, they are available or can be accessed to the other procedures and from the other procedures and so on. However, the procedures or the labels which are defined inside the procedures, just like L2, they cannot be accessed from other procedures or also from the main program and so on. So the local label is visible only to the statements inside the same procedure. So here L2 is accessible inside this procedure, or this label 2 or L2 label is only accessible inside sub2. However, for example, L1 is the global procedure, global label, so we can access this, or we can transfer control, we can access this label L1 from this procedure and from the main program and so on. But L2 cannot be accessed from any other procedure or from the main program, because that is the local label, or that is a label which is inside the procedure. So just be careful when, for example, this jump L2, this will cause error if you want to jump to this local label. However, you can jump to L1 because this is the global label and so on. So the global label are available everywhere, and local labels are available within their procedures and so on. This is the same concept like in C or the C++ and other languages, the scope. So the scope of this local variable is inside the procedure here is limited, and for this global variable their scope is inside the whole program and so on. Now we'll discuss about the procedure parameters. So each procedure can receive some or get some parameters. For example, if there are some good procedures or the procedures who have some accomplish some complex task, what will happen? These procedures are used by other programs, or they are being called by other programs. For example, if we write procedure to perform some array or operations on some array about the strings, about some computation and so on. For example, solution of the differential equation, solution for any matrices and so on, or to store record inside the file and so on. So we write some procedures and save them in the libraries. And some other programs, if these procedures are very good, very fast enough, very efficient enough, and if some other procedures they want to use, other programs they want to use these procedures, then they can call them. So but if it refers to the specific variable names, for example, they cannot use those procedures if they refer to some specific variable names. This is most important thing. Now, for example, if we say that when this procedure refers a specific name like ABC1 is a variable which does it refer, then it will be very difficult. So be careful. We will see the example. So these parameters, they help to make procedures flexible because the parameter values can change at runtime. So whatsoever the parameters, whatsoever the values, or whatsoever the parameters or the variables that you use inside the program, they must be general, not the specific one. For example, from the main program, there is one variable. Its name is the my array, and if I use the same label or same name inside the procedure, then this procedure is restricted to that my array or some array name only. So we have to avoid that situation. For example, here you can see array sum procedure. The name of this procedure, array sum. Here is a procedure. So this array sum procedure, and this is the end of this array sum procedure, and so on. So what we are going to do here, first we ESI, EAX, they are being erased. Their values are being erased, and ECX is the length of array, length of my array. So here you can see my array is the specific name. So there are specific variable names. So for example, my variable must be defined inside the main program, and here we do add EAX my array and ESI, and again we increment ESI and just jump to L1 and perform until the ECX becomes 0 and so on. We already know that this loop instruction decrement the ECX. So here my array is very specific variable name, so we are referring to this specific variable name. So this program is only this procedure is only about adding my array element and so on. So we have to avoid this one, this specific variable name usage inside the procedure. So how we can avoid this one? So as I told you, what if you want to calculate the sum of two or three arrays within the same program? If I want to have my array 1, my array 2, and my array 3, definitely in this case what you have to do, you have to write 3 procedures to sum them, to calculate the sum of these 3 arrays. So because this procedure can sum only my array 1 and so on. So we have to avoid this type of situation and so on. So how we can avoid? So this version of this array sum procedure, it returns the sum of any double word array whose address is inside the ESI. So the sum is written in EAX. So this is the procedure, a very small procedure. What we do, we only remove the EAX, and definitely we have the value, and we know that ECX must have the number of elements, array elements, and ESI must point to the array of double words and so on. So if these are the received elements or received variables which we use inside the array, and ESI must have the ESI must point to the array. So here this simple procedure, so what we do, we use the ESI and we increment ESI and so on, and this procedure is almost, this body is almost similar, the 3 steps. So they will perform execution. So here you can assign the address of array in ESI, any array whatsoever, but it should be double word array, because we are using the EAX or double word to store these elements and perform addition. So these are the 2 things. First, ESI must contain the double word array address or pointer to the double word array, and ECX must have the number of elements, length of that array, and EAX will have the total sum. Here is the flow chart. You can see the flow chart of this array sum procedure. What we do first, there are 2 things that we do first before calling this array. First we do push ESI, push ECX. So we are going to store these 2 elements, and if you are using EAX somewhere else, so people avoid to use EAX in the main program, we store our results somewhere else. So EAX is 0 now, because we have to do this one. Or maybe sometimes what we do, we use this instruction inside the procedure also to remove whatsoever the previous contents are. We just remove this one, and this is the label. So what we do, we use, sorry, this one has come here, so it should be 8 EAX and ESI, and this is the second element, and this is the loop to AS1. So for example, consider this is the whole procedure from here to here. This is the whole procedure. So what will happen, first we push ESI, this is the beginning is shown by this oval shape and so on, and a square shows the processing. And first we push ESI and ECX, we reduce or we remove the contents of EAX or accumulator register. We perform addition of whatsoever the values inside EAX and the value pointed by this ESI. Next instruction is we increment ESI by 4, because we are using the double word, and then we reduce. This procedure is these 2 lines show the loop instruction, loop to some label. So ECX is equal to ECX minus in decrement, and then if ECX is greater than 0, until and unless this loop will continue until and unless ECX is equal to 0. So if it is greater than 0, yes, then again add, perform addition. Otherwise, if it is equal to 0, then what we do, we will pop ECX and ESI, both pop ECX and ESI. So there will be end of this procedure. So this is the flow chart for the array sum procedure. What we do next, there's a pointer is called the uses pointer. So this pointer lists the registers that will be preserved. For example, here you can see there is array sum procedure. Array sum procedure, we define that it uses ESI and ECX. It uses ESI and ECX. So set the sum to 0. So move. We do all this as I told you. We perform EAX or removing all the contents of EAX and assign a new sum. So what we have to do here, if we use uses ESI and ECX, then what will happen, actually these 2 values or 2 registers are being used. So if we define if we put the keyword uses, then MESM will generate the code like this one. Before executing any instruction, these 2 instructions will automatically be added, push ESI and push ECX, and before going to return, it will pop ECX and pop ESI. So this is the purpose of this uses operator. If you want to perform, or if you want to automatically preserve the values of the registers that you want to use inside the procedure. So what we have to do next, the conditions when you cannot push, or when to push and when not to push. Here you can see the sum of the three integers we store in EAX, for example. In the first example, the very first example in the beginning, you saw that we put sum inside the EAX in the line number 3, for example, here 1, 2 and 3. The same example is here, but we pop instructions. The pop instruction here, it will replace the starting value of the EAX on line number 4. So for example, what we do, we push EAX, we put the contents of EAX inside the stack. We store that EAX contents by using push. The next instruction is we add EAX and EBX, so contents have been added. Then ECX is also being added with EAX. And for example, if we perform pop here, it will replace whatsoever the previous value or previous sum value was. It will be replaced by this value, the value before performing this sum. So you have to be very much careful when you can push and when you cannot push. So now what we are going to do here, before going to summarize, we will see how we can perform. So we create a new project and we want to store this project into the E drive, and the subject name, okay, so we just selected this folder and the name is (1601) is the name. So the name of this assembly file is example 1601. So we have defined this one. We just put some directives, and for the Microsoft assembler, include path is MASM32 include. So we just apply. Now what we're going to do, we just copy the skeleton program in next few lectures. We will discuss about this these include directives and so on. So this is the skeleton program. For example, we have three values for here, a double word, or if I write a1 double word, there is no value. And so this is the start and end. Sometimes people just write here, for example, the main procedure, and this to show that this is the main procedure, and here they write main end procedure and so on. So there is no need to write. If you want to write, it's okay. So this will be considered as the main program or main procedure and so on, and everything. So here what we do, we assign move EAX, 01, move EBX, 02, move ECX, 03. Okay, so we just save this one and we define a procedure for example, before going to call or invoke this one, we define a procedure here. The name of the procedure is sum of, for example, sum of is the procedure, and end of the procedure is like the name, same name, sum of and p. So when we call this procedure, it will sum the contents of three registers. So what we have to write here, for we'll write 8 EAX comma EBX, 8 EAX comma ECX. So we have added all these, and then we return. We use the return as instruction here. Okay, we just save this one and we call this one, call sum of. Okay, so this is very simple program. There are three elements and we just add their values or add them to the add their values and so on. So, and the result will be stored in accumulator register. So we just build. Sorry, there is ABX, so this is wrong, so it should be EBX. So we just build it again. Okay, so now it's successful. Actually, I made some mistakes, so it was the ABX, so it should not be ABX, it should be EBX register. Okay, so we just continue. Now, first thing first, okay, it's a bit slow. I'm really sorry. It's a bit slow. Now we just, instruction pointer is up to this point. So this is instruction pointer. We don't need memory right now. We are not using, so we just remove this one. And before this, this is the first instruction that will be executed. I was just confused because it just took longer time to show all these registers and so on. So here, first instruction will be executed. So EX will be equal to 1, EBX will be equal to 2, and you can see instruction pointer here. So instruction pointer is, I will show you the whole execution, but first we will see what will happen when we perform addition and so on and after this call. So the third instruction, so ECX is equal to 3. Now we are calling sum of procedure. We have called this sum of procedure. Now you can see, actually it is not going to that address, but right now you can see here, actually it has performed its execution, and the sum of procedure has returned it has assigned the value 6 inside this EX register. So EX register has the sum of all these three registers, EX, EBX and ECX. So I just complete the execution. Now here you can see, actually the pointer doesn't go here, but actually it performs complete execution and returns back when we go in a step-by-step manner and so on. Even though if you want to do that one, what you have to do, we have to put breaks here. So if I just save this one, build this one, and you can now see. So here it's a break. I just put the breaks here. So after this break, you can see it comes here directly, 8 EX EBX. Then it comes here. Then third is return, and again it return back to the invoke exit process. So I put breaks to show you that actually the control is being transferred, or the instruction pointer has is being transferred to this procedure or not. Maybe I just combine this one and show you how actually it happens. If I just call here this, okay, so here is the call. Okay, so I will just run this one once again, and we will monitor the behavior. Before going to monitor the behavior or before executing, I just build this one, rebuild again, and I will just disassemble the program. Disassemble mean I want to see the instruction addresses or the instruction memory or the program memory or the code segment. So I just run this one, and I just right click here anywhere inside this window, and right click, and there is go to disassembly. Okay, now we are here at the disassembly. Here you can see in disassembly. So first instruction is move EAX01. This instruction is stored at 00DB1010. Instruction pointer has the same address because this instruction still has to be executed. It did not it did not perform execution or started its execution. So after this instruction, the next instruction is this one. So I just execute this one. So it has performed its execution, and 1 has been transferred to EAX. Now EBX is being assigned value 2, and the starting address is 00DB1015. So this is the address which is stored inside the instruction pointer. Okay, so we execute this instruction. Also we execute third instruction. Third instruction is nothing but move ECX3. So 3 is being moved to the ECX. Now here we are at the instruction call instruction, and here you can see sumup has been replaced with the value 0DB102BH. You will see here the first instruction inside the procedure is add EAX EBX. So this instruction is stored at 00DB102B. So the instruction pointer, when we execute this instruction, will be assigned this value. So just look at this value in the instruction pointer. So this instruction pointer has been added a new value is 00DB102B and so on. So now you can see instruction pointer has been added, and also the stack pointer. Now stack pointer is pointing somewhere. Where it is pointing, you can see stack pointer is pointing to the 0042FC04. So just remember, I think we have to disassembly again, and this was the instruction that we have executed. And invoke instruction, exit process and null or exit process 0 is this instruction 00DB1024 is the instruction which we use to execute. So this address must be stored inside the stack pointer. So it means there has been some changes inside the stack pointer. So we just go to this stack pointer address. So we just open the memory in the debug. We have windows and we have memories. So we are going to start with the memory, this one. So the value is okay, so value should be 002410 dB and so on. So the value should be okay, 00 dB, this should be the value 00 dB 10 and 24 because the stack grows in this direction. So the value, this is the address 00 dB 10 and 24. So you can see these contents 00 dB 1024. This is the address which has been stored, and now instruction pointer is pointing to this address because it has been added. When this will be popped, or when the return instruction will be executed, now we are at this point. If we execute, so it has added the contents Now you can see flag register has been changed and instruction pointer has been changed. So instruction pointer pointing to this instruction. Now there is return instruction. When we perform return, there will be pop. I mean, now again the stack has returned back to the previous location, like this one. New location, the new address has been assigned to this. Okay, so we have popped this value and we are calling this invoke exit process. You have seen that the instruction pointer and the stack pointer. So stack pointer and instruction pointer, these two registers are maintaining the program flow control, and we also use the we saw that these two registers, these two areas are being something is going to be saved inside the stack, even though we are not saving by ourselves by using push and pop. But when we call and when we return, so at the time of call, push operation is being performed, and that pushes the or enters the address, which is the next instruction address, and so on inside the stack, and we return, it pops. So it means we are not calling or we are not doing anything by ourselves, but program automatically does. Okay, so what we are going to do next is we are going to open a program, or we are going to save this one. We just close this program. We just close the solution, and we are going to have a new example, file and new project. Example 1602. Now we just add item, not a new item, but we just add existing item. So this item should be I have the program on the desktop. For example, this is the on E drive, sorry, whatsoever the drive at your end is, but here I stored okay. So example array okay. So this is the array sum of the array example. So what we do here, this is the offset or the address of the variable 2. Variable 2 is the name of this array, or we can use the array w. Okay, array w and so on. So we have this, or if we use the array of double word, so this is the array of double word and so on, and these are the values, for example, inside this. Okay, so here you can see we have the total and we have this addition and so on, and we want to do what we want to do. We want to save all this inside the, so ECX has the length of the array. So ECX has the length of the array. So what we do, we will have used the ESI. This ESI has the length of the array and so on, and the, for example, if we use EDI as an offset variable, so we want to create an array, so we just define an array or define a procedure. that sum ARY sum procedure ARY sum and procedure and we do all these things inside this one. So if we say AX is equal to 0, so we EAX is equal to 0 and EX is equal to ESI, okay, and then so this is the variable 2, so we just remove this one, or what we can do, we can say ESI comma EDI, okay, and this is a loop 1 and so on. So we just call the procedure here. So here we indicate that this is the starting of the procedure. Array sum or ARY sum procedure to indicate that this is the starting of this procedure. Here we call this procedure. For example, we call ARY sum procedure. So what will happen, this procedure is a general procedure. You can add any number of arrays whatsoever the array, so we don't need this here. We just remove this exclusive OR statement and so on. So we have move EAX 000 and we remove this one, contents of accumulator, we use ESI, and now the ECX has the length of this array. ECX is the length of this array and so on. So this ECX must have the length of this array, as we know. So this length of array, and we are calling this one. So ECX will serve as a counter, or instead of using variable 2, we have used the name array W. So array W, okay, and now we can use array W. Okay, so we just see how many elements are there. We just remove all these elements, and we want to have few elements to show their sum and example and so on. Okay, we just save this one, we just build the solution. Okay, so array sum, we use ARY sum. Okay, the name is different, it's array sum. Build the solution. So this is now successful solution. Okay, now we just run this program and see, and in the end we will see what is the output. So we just run this one and we just move these registers here, and first of all EDI is the offset address. Actually it should not be EDI. Okay, it should be not be. Okay, we just made one mistake. Now what is the mistake here? That ECX is the length, okay, and EDI has the offset. So here I have to use EDI as offset. So EDI has the offset, for example. So EDI should be added here and so on. Okay, so what we are going to do here, again build again. It should not be EDI here, it should be 4 here. Even though the logic is wrong, but it doesn't give you any error. It doesn't matter what you are going to add in the ESI, because ESI has the offset. Why we're using ESI here, it should be EDI and so on. So if we use ESI, then it should be ESI here, here at this point. ESI is the offset of this array or the starting address. Here we use ESI, and here we also use ESI. Okay. Okay, I will just make this one more logical, but right now we just run this one, or we just build. Okay, we just run, and we can see first is the ESI has the starting address. So ESI has performed its execution. This statement has performed. So array W, actually array W is stored at this point. So ESI has the starting address of the array. If you want to make sure that either it is stored here, so you can go there and see the memory. So we just go here in the memory, and you can see. So all these elements are stored from here. This is the starting address. So it's a little endian. So little endian is here. The least significant byte is stored at the lowest address. Then second element, then the third element, and then fourth element, and so on. So it means that a starting address of the array has been stored. I will change the values, and we can see here. So next instruction has been added, ECX length. We call that so we just break, and we just see what is what is wrong here. So which registers are ESI? So we use the EDI, for example, here as offset, and EDI as offset, because ESI is being okay. So we just build again. Yes, stop debugging. This is the first value, second value, third one error W, and call error sum. So ECX has the okay, so ESI is the average W, is the name is okay. ECX has the length, and EX is okay. So ESI is this one. This okay. So the main thing is we did not write return instruction here. This was the main. So even though we write ESI, EDI, whatsoever, but the main problem was we don't have the return instruction. This was the main problem. So we found this. So okay, now we just start first, second, third instruction. So this is the sum inside the array, you can see. So actually the main problem was we did not write the return instruction. So if you do not write return instruction, then program will continue in this direction, without any sense. So that was the reason it just gave us the error that you are doing something very wrong. You are performing something without any sense. Okay, so now we just come back. Now we are here. Either you use ECI, ESI, EDI, it doesn't matter right now. Actually, I was thinking maybe the ESI or EDI has been used by some other thing or not, but it was not. So the problem was with the, so I'm using EDI, for example, doesn't matter. And if I just run, so you can see here what is inside, 0, 0, 0, 1, and all these. If I want to have another element, this element should be like, so the value inside this element is all these zeros, and here is the 1. So 4 and 4, so this should be 0, and here it should be 1. Okay, so there are 1, 2, 3, 4, 5, 6 elements. I want to make it 8 elements. I need 2 more elements to make it more. I want to make all these ones, so this should be like 1 should be 1. Okay, now here the least significant digit for hexadecimal is 1, then second, third, fourth, 5, 6, and all these. So array will perform addition. So what we are going to do here, or what is going to happen here, we define the offset or the starting address of this array inside the EDI or inside any register which you want to use, either EDI, ESI, and so on. Then ECX has the counter because we are using this ECX inside the loop. Okay, then we are calling this array sum program or array sum procedure, and then the next instruction is exit instruction. What is inside array sum procedure? We just remove all the content from EAX. It has 0. The contents, all contents have been removed, and again EDI is the offset or the starting address. So we are adding the contents in the EAX. We are using constant value, but instead of using constant value we can use any register also. But right now here we are not using any register, but we can use, how we can use, you know the type of subroutine or type instruction. So the type will return the total size or type of the size in terms of bytes. How many bytes a variable occupy. If I write the type return the type of this array W, so it will give you 4. So you can use the same register here automatically. It means we can make it not only for the any array, but we can make it more general to add all the elements of any array. And the registers that we are using are EAX, EDI, and the ECX, and whatsoever the next register you are using. So here we can build, run, and first is the EDI has been EX sum has been installed. Okay, so here there is we did not change properly, but even it's going to sum. What was the problem here? Actually, maybe the sum of the element. So okay, fourth element, fifth element, sixth element, seventh element, and eighth element. So there is some repetition. So was 1 1 1 third. Okay, this should be the fourth. Okay, this is second, third, fourth, fifth, then sixth, seventh, and eighth. Instead of using this one, maybe we can use like this one, 1. Okay, I don't know, I'm not concerned about this one, so we can make it like more generalized. We just save this one. For example, if I want to have another array, Control C, copy, and I want to have another array. I want to store some decimal values, 1, 2, 3, 4, 5, or maybe I can use 1. Okay, so these are the elements, and array 2W, for example. Now I want to add the contents of this one also. So I just copy this whole, copy, and I just paste again here. So this to show you that either this is more general or not. So here you can see I did not make any changes inside the array procedure. Right is array 2 and so on. So I just call array sum. So save, I just build this one, I run. So first EDI and ECX, and then we are calling. So here you will see the sum. Then again I call EDI, I use the array 2, its offset address in EDI, then ECX has a length, and I sum this one. So here is the B. B is 11. So if you sum all these, 1 plus 2 plus 3, so this is 5. So to 6. So 3 and 3 6, and 4 10, and 11. So the sum is inside. So this is more general. Now I want to complete this execution and then make it very much general. Like if you recall that move ESI type array W move ESI type array to W, and here you can see if I use ESI and save, I just build this one, run this one. So again the same here. So this is the same solution, exit process. Now maybe you can say I have used this array of double word. I want to use array of byte, for example. Array B, array of byte, and its size is byte, not word. Its size is byte, and I want to use this byte also. Okay, so doesn't matter at all. You can use any size, array of any size. So array not to array B, length of array B, and array B. Save this one. I just save this one and just build again. So it's okay. So it has executed this one. Okay, so it will execute. Maybe the answer is almost, yeah, this is the new answer. So you can see here the answer is almost similar, same answer. I've just make some modification here. First stop this execution 1. So it should be, answer should be 10. So 3 2 5, it should not be 10, it should be 1 2 3 6 and 8. So answer should be 8 for this one. I just build again and run for the last time, and to show you that this is the array sum procedure, a more general procedure that can array. So this is array sum for the first array sum for the next array sum for the okay, sorry, here we are using the array, but the problem is we are using EAX. So instead of using EAX, we have to use it now. Instead of writing byte, we use, for example, word to make it, to show you that either it's visible or not here. So array B name is similar. We use AX only. So it should be okay. Here the type is ESI or SI, for example. In case of byte, ESI, and this is the EDI. Okay, it doesn't matter. So here's AX only. So just save, just stop this one. We just build the procedure, run this again. First one, second one, third one. So here you can see the answer is 8. So you can make it more general as you want, because the error here was because we were using a whole EAX register and there was some mismatching. So we have resolved this one. So we are using AX in the procedure here. So but one thing, when we use EAX and here EDI is pointing to someone, so there'll be type mismatch. So I think it would be better if we use the only 8-bit and so on. So just be careful when you want to make it more generalized. Sometimes you cannot make it very much general. You need some more conditions to make it more general, like if you want to perform the addition for double word and byte and word size and so on. So first we have to check either the size is either word, double word and so on. So this you should be very much careful. The answer was in this one, for the first array answer was not correct, but for the second and third there was no difference because we were using only the word size. So I think we cannot generalize this size right now because we have to use more condition like if statement and so on, and hopefully we will discuss in the next coming lectures. In this lecture number 16, we discuss about the creating procedures, how we can create procedures. Then we also saw that how we can document procedures, and then we did example of the sum of procedure to sum 3 elements and so on, and then we saw about the call and return instruction, how we can use call instruction and how we can use return instruction. As we know that call instruction calls the procedure and return instruction exits from the procedure, and control is being transferred to the main procedure or the calling procedure or main program. And instruction pointer and stack segment or stack pointer, they are being involved, these two registers, to store the instruction pointer register and so on. Then we discussed about the nested procedure calls, local and global labels, procedure parameters, flowchart symbols, and uses operator, but we did not do the programs in assembly language for these nested procedure calls and so on. And inshallah in the next lecture we will cover these topics in assembly language, and I will come with more examples about the assembly language. So this is end of this lecture number 16. Till next lecture, Allah Hafiz.